So just to kind of recap on what we discussed in the last lecture. So in the last lecture, we had talked about systematic absences for screw axes and centering. So for example, if we review over the axial centering that we discussed, we talked about C centering. And for C centering, we have X, Y, and Z. Goes to X plus a half, Y plus a half, and Z. So this is a symmetry operation, and now we look at only the axes where there was translation. So since X and Y were translated, and Z doesn't change sign, Z is the same coordinate, then our systematic absence for C centering would be looking at the HKL indice and the H plus K indice if it's odd, 2n plus 1, it would be absent. So if you go through the HKL file and you look and you see all of the H plus HKL indices where H plus K is odd, they should be systematically absent for C centering. So for example, a few examples of this, if we have 3, 2, 1, if this would be absent because 3 plus 2 is 5, 5 is odd. It could be even the 300 reflection plane, it would be absent as well because 3 plus 0 is still odd, so this would be absent. And we'll do one more, let's see. And the 120 reflection plane would be absent because, again, H plus K has to satisfy the criteria that when you add them together, it's odd. So that's for C centering. Now we'll look at A centering and B centering before we get to face centering and body centering, which can be a little bit more complicated. So we'll look at, say, B centering. So B centering, we have X, Y, and Z. We get X plus a half, Y, Z plus a half. And so here when we look at it, since since Y doesn't change sign, you have to include the K indices, and we see that X and Z are translated. So again, we have to look at the HKL indices because again, K doesn't change, Y doesn't change sign, so we can't replace it with a 0. It has to include the HKL. And so here we're looking for H plus L equals 2n plus 1, which is odd, and these have to be absent. So whatever you translate, that has to satisfy the condition of being odd for it. So since we translate along the X and Z positions, then it would be H plus L is odd. They have to be absent. And then we'll look at A centering. So in A centering, we have X, Y, and Z. X doesn't change sign. We translate along Y and Z. So here again, since X doesn't change sign, we still have to look at the indices that have H in it. So we have to look at the HKL indices. And we're looking at, since Y and Z translate, we're looking at the K plus L equals odd. These should be systematically absent. So some examples of this: 1, 1, 2 would be absent because 1 plus 2, wait, k plus l, yeah, k plus l, 1 plus 2 is 3, it's odd. We could do the 0, 2, 3. This would be absent, etc. Now for B centering, just to give you one or two examples of this. So it could be the 1, 1, 2 reflection plane would be absent because 1 plus 2 is odd. Or for example, 3, 1, 2 reflection plane would be absent. So with centering, you got to look at the HKL. You got to look at indices that contain the H, the K, and the L, and you're looking at whether or not whatever you translate along, those two indices added together have to be odd and absent. So that tells you whether you have A centering, B centering, or C centering. We'll talk about face centering and body centering in just a moment. So that's what we discussed last time. In addition to this, we also discussed screw axes, and just to kind of go over that one real quickly before we begin today's lecture. So with screw axes, and let's just show you first with a two-fold rotation. So if we have a two-fold, say parallel to B, we start with X, Y, and Z. We get negative X, Y, negative Z. So with a two-fold, there's no translation. So there's no even or odd rule for it to satisfy. So two-folds won't show up in systematic absences because there is no translation along any axis. So you have to have translation in order for those two waves to be out of phase where they destructively interfere, and that's where you get the systematic absence. So a two-fold you cannot determine from systematic absences. But now if we look at a 2 sub 1 parallel to B, so we start with X, Y, and Z. We get negative X, Y plus a half, negative Z. So here, since X and Z become negative, we can drop those indices. So we can just look at those can be 0 for the H indice and the L indice. And since we're translating along Y, we look at the 0, K, 0 indices. And if they equal 2n plus 1 are absent, then you have a 2 sub 1 parallel to B. So for example, the O1, O, or the O3, O, these should be absent because they're odd K values. So that indicates a 2 sub 1 parallel to B. Now if we look at a 2 sub 1 parallel to A, again we have X, Y, and Z. We perform the symmetry operation, so we translate along X, negative Y, negative Z. So since X and Z are, or excuse me, since Y and Z are negative, we just use the indices 0 for them. Since we're translating along X, it's the H indice that's going to determine whether or not it's absent or present. So we would look at the H0, 0 indices, and it has to satisfy the condition of being odd, and these should be absent. So for example, the 1, 0, 0 or the 3, 0, 0 are absent. That indicates a 2 sub 1 parallel to A. Now, it's not just the 1, 0, 0 to 3, 0, 0. We're talking about all the odd H00 indices. So 1, 3, 1, 0, 0, 3, 0, 0, 5, 0, 0, 7, 0, 0, all the way up until however many they have in the HKL file. I'll just give you a few examples of what they look like. Next, we have a 2-1 parallel to B. So we have X, Y, and Z. Since it's parallel to B, we not B, let's do C. We've already done B. C. So X becomes negative, Y becomes negative, and then Z plus a half. So again, since X and Y are negative, they get the indices zeros for their reflection. So we're looking at the 0, 0, L reflections, and this has to satisfy the condition of being odd or absent. And so this could be things like the 0, 0, 1, 0, 0, 3 are absent. Now, if you notice that not only are the 0, 0, 1, 0, 0, 3, and maybe the 0, 0, 2, if you see both even, let's scratch that. Never mind. Yeah. So we're just looking at the odd absence. So this is where we left off in the last lecture. So now we're going to continue looking at face centering, body centering, and glide planes. Those are the last few remaining symmetry operations that involve translation. So with body centering and face centering, again, if we look at body centering, we have X, Y, and Z, then we translate a half along each direction. So since we translate in all three directions, there's no coordinates that are negative, so we have to include all the HKL values. And since we're translating along all three directions, it's the H plus K plus L has to be odd and are absent. That would indicate I centering. So to give you an example, could be the 1, 1, 1 reflection plane. That adds up to an odd number. That would be systematically absent if you had a body centering occurring, or I centering. So again, since all three axes are translated, you have to look at the H plus K plus L equals odd, because you're translating along all three axes. Now with F centering, here we're translating along all the different faces of the crystal. So we have X plus a half, Y plus a half, and then X plus a half, Z plus a half, and then Y plus a half, Z plus a half. So in order for something to have face centering, it has to satisfy all of the following conditions. Now these are the observed conditions here. So if the H plus K even is observed, the H plus L even is observed, and the K plus L even are observed, and the odd are absent, then it's going to be face centering. So if we wrote this for the absence, systematic absences, so we would do the HKL, where H plus K equals 2N plus 1 are absent. HKL, H plus L equals 2N plus 1, absent. And then HKL, K plus L equals 2N plus 1, absent. So all three of these have to be systematically absent for you to have F centering. So here are the odd. The odd are the ones that are absent. So if we have the HKL where the H plus K is absent, and the HKL where H plus L is absent, odd, and then the HKL where K plus L is absent for the odd, then we have face centering. So face centering has a very restrictive set of absences that must be observed for you to have face centering. It has 3 sets of absences that have to occur together for you to observe face centering. So for example, for the first criteria, if we had the 1, 2, 1, it was absent, and then also the HL 1, 1, 2 were absent, and then the actually the 1, 1, 2 would work for both the H plus L and the K plus L, but let me give you another one. Let's see. K plus L. 3, 3, 2. So if all of these reflections were absent for the odd, then you would have F centering. So that's pretty much all the different systematic absences you can have for centering. Again, you have to look at the entire HKL because there's none of the directions become negative, so you have to include all the indices in your condition. So this is just kind of an overview of what we just talked about. So for reflection condition, this means it has to be observed. For systematic condition, it would just be the odd. So whenever you see reflection condition, that's for the even ones, they have to be observed. The odd ones would be systematically absent. So for the H plus K plus L even, they would be observed, but the H plus K plus L odd would be systematically absent. So people use either one. Reflection condition means they're observed. Systematic absence means for the odd, they're not observed. And so even for R centering, you have this type of condition as well, too. So we've talked about screw axes, so I'm not going to dwell too much on this one because we've gone through this pretty much in depth. So we've already discussed the different screw axes along the different axis of rotation. And so here, if we look at this snippet of an HKL file, we want to know, is there a screw axis present? So what we want to look at is we want to look and see, since these are all H0 and L0, since only K is present, this means we're translating along the B axis. And since H and L are 0, the X and Z coordinates are becoming negative. So since X and Z are negative, K is translation. This could be showing us that a screw axis is present. So what we have to look at is, if we think a screw axis is present, look at the odd O0, K0 reflections and see if they're absent. So we get to the first, we have -4, 4. Those are even. We don't have to worry about them. But notice the intensity, 841, 843. And then when we get to the odd reflection, the 0, -50, we have 0.75, 10.38, and 9.32 for the 0, -50, and 0.50 reflection. Now these do have some intensity associated with them, but when you compare them to the even reflections, you'll see that the even are a lot greater than the odd. So from this, we would deduce that this 0, -50 would be systematically absent, and the 0.50, because their intensity is very small, compared to the intensity of the even reflections. Secondly, you'll notice for the error associated with those intensities, for 0, -50, the observed intensity is 0.75, the error is 1.49. So this is kind of like noise for this reflection. Intensity is 10.38, the error is 4. So these are not very strongly or very intense reflections. These are very weak, indicating that they're probably not even present. Then when we go to the 0, -60, 0, 60, you'll see again we have very intense reflections with reasonable error associated with it. When we go to the 0, -7, and 0, 70, you see that our intensities are very small and our errors are very large in respect to the intensity. So this is a good indication that these set of reflections are not present, because you got to compare it to the others and look at the magnitude of the intensity to show you that, hey, this one is probably not present. It's probably just noise that it picked up. And then we go to the 0, -8 and the 0, 80. You see again we have very strong intensities with very small error in comparison to the magnitude of the intensities. And now we go to the 0, -90 and 0, 90 reflections, and again you see we have very low intensity and very high error in relation to the intensity. So this would be a good indication that this set of reflections are absent. And so since the odd OKO reflections are absent, this would be a 2-1 parallel to B. And this is what the computer does when it's looking for systematic absences. It looks at all the reflection data and says, okay, what's the intensity of the reflections for the odd OKO, the even OKO, and then it makes a decision to see whether it's systematically absent or not. And sometimes the computer does make mistakes, so that's why you need someone there sitting at the wheel to look over it. So in summary, this is for the screw axes. The same conditions would hold true for if you had a 4-fold screw axis, a 3-fold screw axis, etc. And again, these are the reflection conditions. So if we were looking at the systematic absences, we would look at the odd. So it would be 2n plus 1, 2n plus 1, 3n plus 1, etc. So the even are what's observed. The odd reflections would be what is absent. So you can have reflection condition or you can have systematic absences. Either one will work. So now what we're looking at is what we have are glide planes. This is the last type of symmetry involving translation. So here if we have a C glide perpendicular to B, well, B becomes negative and we translate along the Z axis. So we put it into this structure factor equation. It simplifies down to this expression here, which is 1 plus -1 to the L. And again, if this L is odd, then this becomes 0. If it's even, it's going to be a non-zero number. So for glide planes, since we translate along one axis and only one other axis becomes negative, for example, for a C glide perpendicular to B, we're looking at the HOL reflection. And the condition L tells us which one we translated along. So we have the HOL reflection, and the condition is L has to be odd. That tells us that H no change in its sign. Y had a change, and L, there was translation. So we can reconstruct this symmetry operator to be X negative Y Z plus a half. So by looking at the systematic absence criteria, you can actually reconstruct what type of symmetry operation it is. So for the HOL, we're looking at a C-glide perpendicular to B. Now, for example, if we're looking at a C-glide perpendicular to A, how would that change the reflection condition? So again, we start with X, Y, and Z. C-glide perpendicular to A means X is negative, Y is unchanged, Z plus a half. So you see we translate along Z, X changes its sign. So since X changes its sign, the indice would be 0 for H. So this would be the 0, K, L reflections that we look at. And when it equals 2n plus 1, these are absence, then you have a C-glide perpendicular to A. Excuse me. So L has to satisfy the odd criteria. L is 2n plus 1. So what type of reflections are we talking about? So for example, 0 to 1 would be systematically absent because the L is odd, or the 0, 1, 1, because L is odd, is going to be systematically absent for a C-glide perpendicular to A. Now, if it's a C-glide perpendicular to B, again, we're looking at the H0L reflections, where L is has to satisfy the even or odd criteria. So L equals 2n plus 1. These are systematically absent. If I can spell absent right. Let's see, absent. So for example, these could be the 1, 0, 1, because their L is odd, or the 5, 0, 3, L is odd. So all of these would be systematically absent. So the one you translate along is the indices that has to meet the criteria of being odd to be systematically absent. The one that you become negative, it becomes a 0 indice in the systematic absence criteria. And then, since in the case of C-glide perpendicular to B, X doesn't change sign, so X still remains, but it's not involved in the criteria of meeting whether it's systematically absent or not. So this is how glide planes work. Notice the difference between a C-glide perpendicular to B is the HOL reflection, and when we did a 2-1 parallel to B, we were looking at the 0K0 reflections. So notice the difference between the two sets of conditions. So the 0K0 was for the 2-1 parallel to B, but when we have a C-glide perpendicular to B, we're looking at the H0L. Another thing to note is that for screw axes, only one indices is non-zero. For glide planes, 2 of the indices are going to be non-zero. So this is just a kind of an overview of the systematic exceptions or absences for the glide planes. So we have a C glide, we have a B glide. So B glide is very similar to C glide. So for a B glide, if we have it perpendicular to A, so X changes sign, we translate along B, the y-axis, and Z remains the same. So for the, we'll be looking at these 0, K, L reflections. And so if the 0, K, L, and since K is what we're translating along, it's the one that's going to meet the even or odd condition. So if K is odd, it's going to be systematically absent. If K is even, it'll be present. That indicates a B glide perpendicular to A. Now for a N glide, if you remember from N glide, we have translation along two axes, and only one axis changes sign. So for that one, we'll be looking if this is an N glide perpendicular to C. We translate along A and B, so we'll be looking at the HK indices, and since C is negative, it'll be the HK0. And so if the HK0, where H plus K is odd, these should be absent. Again, this has to be H plus K because we're translating along two different directions. When it was a B glide perpendicular to A, we're only translating along one direction, so therefore only one of the indices has to meet the criteria of being odd. So always the indices or indices that you're translating along have to meet the even odd criteria to be either observed or absent. It's only the, again, the axes that you translate along those indices are what have to meet that even odd criteria. If there's no change in the sign of an axis, you just have to keep the indices, but it doesn't have any effect on the criteria to be present or observed or absent. So here let's look at a few examples. So we want to know what are the reflection conditions for the following glide planes. So here you'll notice it says reflection conditions. So those are going to be the even conditions. So what reflection should be observed for an A glide perpendicular to B and a C glide perpendicular to A. So again, since it says reflection, we're looking at the even conditions. So here we have an A glide perpendicular to B. So if we have X, Y, and Z, we do an A glide perpendicular to B. We translate along X, Y becomes negative, and Z remains unchanged. So since we translate along X, we have to include that indice. So that's going to be the H indice. Y becomes negative. We just, for that, the K indice, we put a 0. And Z doesn't change. We still have to include the L indice. So we're going to be looking at the H0L reflections. Now, what has to meet the criteria of a reflection condition are the ones that where translation occurred. So since we're translating along the X direction or the H indices, the H has to meet 2N to be observed. Only the even HOL indices, where H is even, are observed, then you have a glide perpendicular to B. So for example, this could be the 2, 0, 1 indice. If that's observed, and only the even are observed, you have a glide perpendicular to B. Now if we look at a C glide perpendicular to A, we start with X, Y, and Z. So since we're perpendicular to A is going to be negative, so negative X, Y remains unchanged, Z plus a half. So now we want to look at the indices. Well, since x becomes negative, we don't have to worry about the h indices. That's going to be 0. Y, there's no change, so we have to include it, k. And z, we translate along, we have to include that, that is L. So we're looking at the 0, k, L reflections. Now, what has to meet the even or odd criteria? Since z is what we're translating along, L has to meet the criteria of being even observed. So if all the even L, OKL reflections are observed, this tells you that you have a C-glide perpendicular to A. So for example, the 0, 3, 4 reflection. That would be an example of an even L, and if that's observed with all the other even L's for the 0KL, then you would have a C-glide perpendicular to A. So when it's talking about reflection conditions, you're looking at the even of those indices that have to meet the criteria. Now, on the next one, we're talking about systematic absences. Now we're talking about the odd indices. So here we have a B-glide perpendicular to C. So we start with X, Y, and Z. Now a B-glide perpendicular to C, there's no change in X. We translate along Y, and Z changes sign. So now we want to see what indices we have to look at. Well, we have to include the X, the H indice because X doesn't become negative. We have to include the Y indices because Y didn't become negative. And for the L indices, since Z became negative, we just put a 0. So we're looking at the HK0 reflections. And since Y was the direction we translated along, it's the K indices that has to meet the criteria of being odd. And so if the odd K's are absent, then we have a B-glide perpendicular to C. So an example of this, the 1, 1, 0 reflection. Because K is odd, this should be systematically absent. Lastly, we have an in-glide perpendicular to B. Again, we have X, Y, and Z. So an in-glide perpendicular to B, so that means we translate along the A and C directions. So we get X plus a half, B becomes negative, negative Y, Z plus a half. So now when we're looking at the Miller indices or the HKL planes, since X was translating along, we have to include the H indice. Since Y became negative, we don't have to look at that K indice, we replace it with a 0. And since Z is translated along a half, we have to include the L. Now to meet the criteria, since both X and Z translate, we have to include both of those. So it's going to be H plus L equals odd. These have to be absent. So an example of this could be the 1, 0, 2 reflection. Because 1 plus 2 is odd, that should be systematically absent. Again, to recap, the direction that becomes negative, you replace that indice with a 0. The direction where there's no change or you translate, you have to include that indices. Now to meet the specific observed or absent criteria, that depends on what directions we're translating along. So for the B-glide perpendicular to C, since we're translating along B, then the K indice is what decides whether it's absent or not. And so for the odd K, for the HK0 reflections, those should be systematically absent. So it's whatever you translate by has to meet the criteria of being odd for systematically absent or even, meaning it's going to be observed. So just to kind of review how you should do this. So it's always good to write the symmetry operation. So to determine what X, Y, and Z coordinates become negative, which ones you translate through, etc. Then from there, you can determine which HKL reflection series would be important based on which X, Y, Z coordinates stay the same, become negative, or translate. So for example, if you have a glide plane perpendicular to B, you would look at the HOL reflections. Now, depending on which axis you translate along, that's the one that's going to satisfy the even or odd criteria. So once we know the class of reflections, then we determine which ones are subjected to the reflection or extinction condition. So if we have a C glide perpendicular to B, it would be the L have to be odd to be systematically absent. Or if it's a screw axis along C, it would be the L that would have to be odd to be systematically absent. And so again, we use these interchangeably, but if we're looking at the odd reflections, those have to be extinct or absent. If we're looking at the even reflections, they will be observed. So you can look at either or. I think the absent is easier to look at than the observed, but it's whatever you want to look at. So if you go through and you see all the odd of a particular reflection are absent, that's an indication that you may have this symmetry operator present. If you see only the even are present for a particular HKL family, then that tells you maybe you have this particular symmetry operator present. And this is just an overview about what we just talked about with glide planes. So for D-glide, it's not a very extensive list because it's actually longer than for this for D-glide. But we're not going to look at D-glides per se. We're mainly going to look at A, B, C, and N-glide reflections or symmetry operators. So now we get to the point of using this to determine the space group. And so if you go and you get a chance to look at the International Table of Crystallography, Volume A, Table 3.2, it actually shows you what criteria, and in this case, what reflection conditions need to be present in order to observe a particular space group. So let me just kind of go through this a little bit. We'll start with something simple, like for example, space group P21. So if the only thing you see in a extinction condition is the OKO reflections where K is odd or absent, this indicates that you only have a screw axis. So if you only have a screw axis and you're in monoclinic, the most obvious space group would be P21, or it could be P21 upon M, because remember M doesn't show up in the extinction conditions, only the 2(1). So how would you determine between P21 and P21 upon M? So you've narrowed it down from 230 space groups to 2 space groups. And if you notice, there's something different between both of these space groups. P21 is non-centrosymmetric. P21 upon M is centrosymmetric. And so there's actually a calculation that's done to determine if a data collected on the crystal, does it tend more to be non-centrosymmetric or centrosymmetric? And from that, they can determine whether it's going to be P21 or P21 upon M. So if you try to solve your crystal in the centrosymmetric space group and it doesn't work, then you should go to the non-centrosymmetric space group and see if you can solve it better. And that's how you can determine the difference between P21 and P21 upon M. Again, they do a calculation, and we'll show you that in the coming days, that you can look at and it tells you whether it's going to be centro or non-centrosymmetric. But sometimes that calculation can be a little bit dubious. So it's best just to try both space groups and then see which one gives you the better model. Typically, they go with the centrosymmetric first in the space groups. So now if we look at, say, let's look at P21 upon C. So for P21 upon C, let's say we look at the HOL 00L where the L odd is absent. So those conditions are met. Where is it? Right here. So here for the HOL, the H00 or the 00L where L is odd are absent, and we have an OKO reflection where the odd K are absent. This indicates that it's P21 upon C. So the HOL where L is odd, what that denotes is a C-glide perpendicular to B, which is what 2 sub 1 upon C has. Now the 00L is just a subset of the HOL where H is 0. Doesn't necessarily mean that you have a screw axis parallel to C. It's just a artifact of being that you have H0L. The L is odd. So this is like in the same family as H0L. So this tells you there's a C-glide perpendicular to B. And then the OKO tells you that the K is odd, tells you you have a 2 sub 1 parallel to B. And that can only be the space group P21 upon C. So sometimes you can narrow it down to one space group. And we'll just look at one more. Here we have a C. So if we have the H plus K, where the HKL and H plus K is odd, that tells us we have a C-glide, or C-centering, sorry, C-centering. So again, the H plus K for the HKL, where H plus K are odd, tells us it's C-centered. Now again, the HKO or HK0 reflections are like a subset of that. So that doesn't necessarily tell you that you have a another type of centering. It's just the same family of reflections, just L set to 0. Next we have the HOL, where H is odd. So that tells us if H is odd, tells us we have a, let me see if I can get this. Trying to find it. Let's see. I'm on the right track. Gotta look. So if H is odd, it means we would have a screw axis parallel to A if it was the H00, or it could be a glide plane an A glide perpendicular to B for the HOL. But you'll see here that for C2 upon M, we shouldn't observe any type of screw axis or glide plane. So what happens is since the H plus K odd or absent, when you have, if H is odd and K is 0, is going to be an odd number, they're also going to be absent. And when h is 0 and k is odd, it's still going to be h plus k is odd absent. So this doesn't mean you have a screw axis present. It just means you have C centering, and these are actually subsets of the original reflection condition. Now if we go to C2 upon C, there we have a C glide perpendicular to B. And so if we look at the HOL, where the H odd tells us that we have a so the H would tell us if that was odd, we have a glide perpendicular to B, but that doesn't make sense. Again, the HOL where H is odd, or the H00 where H is odd, is just a artifact of the original reflection condition. So this can get kind of hairy to see, especially with C centering and A centering, what types of conditions are present. But then we have a HOL where L is odd. Now that makes sense because then we have a C glide perpendicular to B. And so there is a space group with a C glide perpendicular to B, and we can narrow it down to CC or C2 upon C. Again, the OKO, where K is odd, is part of the main reflection condition for C centering. So we'll use systematic absences and the reflection conditions to determine the space group. And this is we use the table of that table I just showed you. It contains all the reflection conditions for each space group. So again, reflection conditions are when they're even, absent conditions are when they're odd. Now, if you don't see a reflection condition, then there's no restriction for that class of reflections. So for example, if we have a monoclinic crystal that the following reflections were not observed, so we didn't observe the 0K0, we didn't observe the H0L, where L is odd, and we didn't observe the 00L, where L is odd. What is the space group? And so what we have to, and this is what I was telling you with the C centering, is that the 00L is actually a subset of the H0L. So if we were to look at all the different operators here, if we have a 0K0 and it's odd, this means it's a 2 sub 1 parallel to B. Because 0K0 where K is odd means it's a twofold 2 sub 1 parallel to B. And then we have a H0L where L is odd. And so what does this mean? This means since L is odd, we translate it along the L and we made B negative, so this would be a C glide perpendicular to B. Now we look at the 00L. And if we look at the 00L where L is odd, this would be a 2 sub 1 parallel to C. But this doesn't make sense because in monoclinic crystal, the main axis is B axis. So what this tells you is that since the fact that the 00L where L is odd, this is a subset when H is 0 and L is odd, is going to be systematically absent. It doesn't mean that it has the 2 sub 1 parallel to C. It's a mere subset of the parent reflection group. So when H is 0 and L is odd, it's still going to be absent, and it may throw you off and think, hey, there should be a 2-to-1 parallel to C, but this cannot be so because we're in monoclinic crystal system, and the major axis is the B axis. So the 0, 0L is a subset of the H0L. And so since we have a 2-to-1 parallel to B and a C glide perpendicular to B, and there's no centering, this would be space group P21 upon C. So we looked at P21 upon C. So here it has no HKL conditions. That means it can be, doesn't have any centering, so it's going to be primitive. So that's what this means. It's going to be primitive. Then we can have two conditions where we have the L is odd. So it can be the HOL where L is odd, or the 00L where L is odd. So it meets those two conditions. And then we have for P21 upon C, the 0K0 where K is odd. So therefore we have P21 upon C. Now if this reflection condition here wasn't present, then we would just have either PC or P2 upon C. So again, here we have a non-centrosymmetric and centrosymmetric space group. So we would try both of these to see which one is the correct space group if, for example, there was no OKO restrictions. So for an example of an orthorhombic space group assignment, let's go through this and see if we can identify this. So here we have an OKL where K plus L is odd. So since K plus L is odd and the H is 0, this tells you it's an n-glide perpendicular to A. Because the H is 0, that means X was negative, and K plus L means they're both translated. So this is an n-glide perpendicular to A. Next we have the HOL, and here we have the HOL where H is odd, K is 0, and L doesn't have to be, it can be even or odd. So since K is 0, that tells us that Y became negative. And since H is the only one that has to meet the odd criteria, that tells us we translate it along X. So this is going to be an A glide perpendicular to B. So we're kind of working backwards to determine what types of symmetry operations were performed. Next we have a H00 where H is odd. So since both K and L are 0, that means they became negative, the Y and Z. So we rotate it. And then since H is odd, we translate it along X. So this is going to be a 2-1 parallel to A. Next we have 0K0. K is odd. So since K is odd, that tells us we translate it along the Y. And since H and L are 0, those became negative. So this would be a 2-1 parallel to B. And then the 00L where L is odd. So H and K are 0, indicating that the X and Y became negative. We translate it along L. This is a 2-1 parallel to C. And so here it says what reflections are subsets of larger groups of reflections. And so the reflections that are subsets of larger groups are the H00, which is a subset of the H0L. The 0K0, which is a subset of 0KL, and then the 00L, which could be a subset of H0L or 0KL. So those are the reflections that are subsets of larger groups. Now, which symmetry operation can correspond to the reflection conditions of the two larger groups of reflections? That's going to be our n-glide perpendicular to A and A-glide perpendicular to B. So now, what are the possible space groups? So this is an orthorhombic crystal. So there are three unique axes, A, B, and C. And so we know that since there's no centering, we know it's going to be a primitive space group. We know that we have an n-glide perpendicular to A, so maybe it's going to be Pn, n-glide perpendicular A. We have an A-glide perpendicular to B. And then it could be we have a 2-1 parallel to C. So this could be a possible space group that would satisfy these conditions. Again, we know it's primitive because there's no centering. We know it's an n-glide perpendicular to A because that was one of the larger groups of reflections. It wasn't a subset, so we know for sure there's an n-glide. We know for sure there's an A-glide. And we still have one more axis, the C-axis. And the only operation that was on the C-axis is the 2-1 parallel to C. So then it would incline us to predict that there would be a 2-1 parallel to C. So this suggests that it would be Pna 2-1. So let's see if we're right. So let's clear this. So the OKL where K plus L is odd meets all of these, meet that condition. The HOL where H is odd, these four space groups meet this condition. The HKO, there's no condition, so we can skip that. And then we had the odd conditions for the HOO, the OKO, and the OOL. And so the only set of space groups that would fit this criteria is the Pna 2-1 or the centrosymmetric version, which is the Pnam. So we picked the non-centrosymmetric version, but if we were to include a mirror plane perpendicular to C, then that would be the centrosymmetric version of that set of reflection conditions. And so you would have to try both space groups to determine whether it's going to be centro or non-centrosymmetric. All right. So how do we distinguish between centro and non-centrosymmetric space groups? This is based on the intensity data. So here it says centrosymmetric crystals have diffraction patterns with higher intensities but more unobserved reflections. Could be due to the molecular packing. Whereas non-centrosymmetric space group crystals have more observed reflections but weaker overall scattering power. And so what we look at is this thing called E² - 1. And so when you're going through and processing your data, it does this calculation. And if your e squared minus 1 is closer to 0.736, it's non-centrosymmetric. If it's closer to 0.968, it's centrosymmetric. So you can see, obviously, if it falls somewhere in the middle, it would be hard to determine whether it's either or. So you'd have to try both. Types of space groups. So they can do a Kurtz experiment, which is second harmonic generation, to determine if it has a center of symmetry or not. And if it's a chiral compound, typically it lacks a center of symmetry, so you would determine that the space group would be non-centrosymmetric. Another way you can distinguish between centrosymmetric and non-centrosymmetric is to try, a bunch of different space groups. So if you do non-centrosymmetric first, but you see from the non-centrosymmetric, does it look like there's more symmetry than what you've described for it? Then you can always go up to centrosymmetric. So that's why you have platen. Platen will convert non-centrosymmetric space groups into centrosymmetric, because you can go up to higher space groups. You can't go back down to lower space groups. So that's one thing you can do, is solve it in non-centrosymmetric and then use something like platen to convert it back to centrosymmetric. If you feel that there's more, if you see a center of inversion, then you can always do that. Now, if you try to model something in the centrosymmetric space group, but it's not working out right, it could be that the molecule is supposed to be a benzene ring, but it looks distorted, or some of the bonds are longer than others, or you have what's called a Flack parameter. We'll talk about that when we talk about twinning. Then maybe you shouldn't be centrosymmetric. You should model it in non-centrosymmetric space groups. So there's all these things you can look at to see whether it's supposed to be centro or non-centrosymmetric. But in summary, though, centrosymmetric crystals are a lot more common than non-centrosymmetric crystals. But if you have a chiral compound, most likely it's going to be a non-centrosymmetric space group if it's an enantiomer pure compound. So some things that can lead to incorrect space group assignment, and this will pop up when you do what's called a check CIF. So check CIF searches to see that you have the correct space group assigned. And so one of the most common ones is missymmetry. So you assign it a lower space group because you think it has less symmetry than it actually has. You have, incorrect or missing hydrogen atom assignment. Maybe you label something a hydrogen that it wasn't a hydrogen, or you label something, you forgot to label a hydrogen, and this can mess up the symmetry in the crystal, especially if you label an atom incorrect. That can mess up the symmetry of the crystal, which could cause you to be in a lower space group than you actually should. Another thing is if you have an unidentified inversion center, this can mess with the bond distances and thermal parameters. The other one is borderline cell parameters. So what this means is that you have a set of lattice parameters. The beta angle is like 90.105, and you say, hey, this should be orthorhombic, but in fact it should be monoclinic, because that beta angle is kind of on the border between being orthorhombic or monoclinic. So you assigned it orthorhombic, but you see that the structure looks kind of wonky in that space group, so you're going to go back and try monoclinic. Another thing is people like to solve inorganic structures in P1, but hardly anything crystallizes in P1 space group. Don't always assume that everything is P1. Also, for C-centered, a lot of times you want to solve it in CC, but CC is a very uncommon space group for crystal structures. Another common one is C2 upon C, which is one of the 5 most common for organic structures. So this is just showing you the pearls of what's wrong with CC. And these are the space groups that have the most probability of being assigned wrong. So CC, PC, P1, C2. So you don't want to just arbitrarily assign one of these space groups. You want to investigate to make sure it is supposed to be CC or C2. So the most common 2 errors, you get the wrong crystal system. Maybe you assume it's monoclinic, it should be orthorhombic, or you solve it in a non-centrosymmetric space group and you realize it has an inversion center, so it should be centrosymmetric. And the last bullet is important. You know, if you solve a structure in a highly unusual space group, you should double check to make sure it is in the correct space group. So you get some of these exotic space groups, you solve your structure, it may solve correctly, but it may not be the right space group. Okay. So on that note, let me see if we have, is that it? Oh, let me just cover this last slide and then we'll stop. And so you may have noticed that there were some bold space group symbols. Those indicate the standard or conventional setting. So space groups especially, they have standard and non-standard settings. So PNMA is the standard space group for all of these different non-standard settings. And so that's why some of the space groups were boldened and some were not. So the bold is the standard setting. The other ones for that same space group number are the non-standard settings. So there's nothing wrong with using non-standard settings, but that's the difference between the two. Secondly, you may know that in P21 upon C, we can also use P21 upon N. And the way we use, or when we use P21 upon N is when the beta angle for P21 upon C is greater than 120. We can translate the C glide into an N glide, and then we can have a beta angle that's less than 120. So P21 upon N again is used when the beta angle for P21 upon C is larger than 120. So that's why you may see P21 upon N or P21 upon C. So on that note, that concludes structure factors. So the lecture for today, I'll stop the lecture and then you can ask questions if you like.